Hello everyone, my name is Satyajit Pattnaik and welcome back to my channel. We all know how important statistics is for data analytics, data science and AI. It is basically the building block. And I hope you already know that we have launched a end-to-end statistics series that is going part by part every Saturday. And welcome to this video. This is the part 3 of the end-to-end statistics videos related to data analytics and data science. Well, statistics is a very vast topic. People usually go for bachelor's degree and master's degree, but we have actually compressed the most important concepts that we usually use when it comes to data analytics or data science. Many of the topics has already been covered as part of part 1 and part 2. In case you have not watched it, links will be in the description. Please go ahead and watch it. In this video, this is the part 3, not the final part, but we will be coming up with another part 4, which will be on some practical applications. However, sticking to this part is all about the advanced topics into statistics. We have covered all the basic things. Now, what is correlation? What is covariance? How do we use it practically? What is hypothesis testing? What are the different types of tests that we do in the field of data analytics? Everything will be covered in this video. Stay tuned and please don't forget to like, share and subscribe the channel. And let me know if you have any questions, any doubts related to the field of statistics or data analytics, data science and AI. Let me know in the comment section and I will do a dedicated video on that topic. See you in the video. In this video, we shall be talking about covariance. What exactly is covariance? Covariance is simply a statistical term that refers to a relationship between two random variables on how one variable changes would impact the other one. In simple terms, if you are analyzing two features or two variables, let's say height of a customer and weight of a customer. This could be your height, this could be your weight. Now obviously when you start plotting the points, this is how the points looks like. In this case, it's quite evident that when the height is increasing, the weight is also increasing, right? So covariance basically helps you to find the relationship between two random variables. Covariance values can range from -infinity to infinity. Positive covariance denotes a direct relationship and is represented by a positive number. So if you find the covariance between two particular parameters or two particular variables is positive, then you can say that it is positive covariance. If one variable is larger, then other one is also larger. If one variable increases, the other increases. If one variable decreases, the other variable decreases. Similarly, a negative covariance indicates an inverse relationship between the two variables. If one variable is larger, then the other is smaller, and vice versa. The value does not represent the magnitude of a relationship, only the direction matters. So, as I said, the values could range between -infinity to infinity. And from this point, it is clear that the magnitudes are not that important. What's important is that if the covariance value is positive or negative. If it is positive, then simply there is a positive correlation or positive covariance between two variables. I talked about a term called correlation by mistake, but we will be talking about correlation in our next slides. So let's just focus on covariance. Okay, so when it is positive, then means it's a positively covariance between two variables, and if it is negative, then negatively covariance. Now just imagine you are dealing with four features x1, x2, x3, x4. The covariance between them is 5. The covariance between them is 10. Can we say that this is a stronger relationship? It's not that. It's not the case. As I told you, that magnitude does not matter. Whether x1 and x2 is a stronger relationship or x3 and x4 is a stronger relationship, that is possible to find out using another concept called as correlation, which we will study. But covariance only tells us whether they are positively covariated or negatively covariance. We'll try to go ahead to the next slide where we will talk about the formula. Covariance formula looks pretty complicated, but it is very simple. Now the formula here is 1 by n summation of I equals to 1 to n xi minus x bar multiplied with yi minus y bar. So this basically is yi. Now xi is nothing but your first variable. Yi is nothing but your second variable. X bar is nothing but the mean of x. Similarly, y bar is nothing but the mean of y. This is a summation symbol. That means if you have 5 numbers, 5, 10 and 15, the summation of this will be a combination of all. 5 plus 10 plus 15, right? And we have 1 by n. Again, this formula changes from population to sample. I hope you remember about population data and sample data. In case of population, it has to be 1 by n. In case of sample data, it has to be 1 minus n minus 1. Okay, so we have mentioned here 1 by n, assuming that we are talking about population. But in case we go ahead and solve a problem using a sample data, then our formula will change. Right? Now, going ahead and talking about an example. So this is an example, stock market movement of two relevant stocks in the same industry. So we have 5 days of data. It is quite obvious that it's a sample data. In that case, our formula becomes covariance of x comma y becomes 1 by n minus 1 summation of x minus x bar multiplied with y minus y bar. Okay. Now, let's try to draw a small table. So we have day, stock 1 and stock 2. So this stock 1 is nothing but my x and this is nothing but my y. These are my two variables, two stocks, and between these two stocks, our main aim is to identify the covariance, whether it is positively covariance or negatively covariance. So I'll try to rub everything off from the screen. So here I'm going to mention x, here I'm going to mention y. So x is 3%, 2%, 6%, 1% and 0. Y is 5%, 4.5, 9, 1 and 1. So writing down the formula again, my mistake of rubbing it off, 1 by n minus 1 summation of x minus x bar multiplied with y minus y bar. So first thing is I have to find x minus x bar and y minus y bar. Before that, let's try to find what is x bar and what is y bar. X bar is nothing but the mean of x. Simple. The mean of x here is going to be 3 plus 2 plus 6 plus 1 divided by 5, which is 3 plus 2 5 plus 1 6 plus 6 12 by 5, which should be 2.4. 5 plus 4.5 plus 9 plus 1 plus 1 by 5. 5 plus 4.5 9.5, 18.5 20.5. 20.5 divided by 5 should be 4.1. So this is my 2.4 and 4.1. Cool. Now we have to find x minus x bar. So for the first record, what will be x minus x bar? It will be 3 minus 2.4, which is 0.6. 2 minus 2.4, which is minus 0.4. 6 minus 2.4, which is 3.6. 1 minus 2.4, which is minus 1.4. 0 minus 2.4, which is minus 2.4. Clear? Similarly, we will do it for y minus y minus y bar. 5 minus 4.1, 0.9. 4.5 minus 4.1, 0.4, 9 minus 4.1, 4.9, 1 minus 4.1, minus 3.1, and minus 3.1. Clear? Now what we will do is we will add it, like we will do the product of this one and this column, of this column and this column. We will do the product. That means we will multiply them. So 0.6 multiplied with 0.9 is 0.54. 0.4 minus 0.16. 3.6 multiplied with 4.9. 36 multiplied with 49. 36, 40, 720, 1440. 17.64 is what I guess. 3.6 multiplied with 4.9. Yeah, 17.64. 17.64. 1.4 multiplied with 3.1. So 14 multiplied with 31. Okay, you can use the calculator for this one. It should be 4.34. And negative, negative, positive. Okay, the multiplication of two negative numbers is always positive. Similarly for this one, 2.4 into 31, 24, 30, 48, 72, 720, 744, 7.44. Okay, that's my 5 numbers, right? So this is being calculated. Now what is this parameter? That means sum of all these numbers. So we'll sum it up. The sum of all these numbers is 0.54 minus 0.16 plus 17.64 plus 4.34 plus 7.44 divided by 5. Now we'll not divide it by 5 right now. Let's just calculate the whole sum. Okay, we'll take the help of calculator. The whole sum is coming up to 29.8. Okay, now we will try to use the covariance formula. Covariance of xy is equals to 1 by, this is a sample data, so we'll consider n minus 1, summation of x minus x bar multiplied with y minus y bar. 1 by n minus 1 multiplied with this thing. This entire thing is 29.8. Now this becomes 29.8 divided by 4, which becomes 29.8 divided by 4, which becomes 7.45. And this is your covariance between stock 1 and stock 2. Looks like a positive number, so it's a positive covariance. That's all about this particular topic on covariance. I hope you understood the basic concept behind covariance and you understood how to solve a problem and how to find the covariance given to features. If you have more features, then you can simply calculate in the same fashion. But honestly speaking, when we jump into the future topics related to Python, pandas and all those things, you can simply find covariance and various other statistical concepts using just one line of code. So do not worry, that is how the programming languages help you. Now that's all about this particular topic on covariance. In the next video we shall be talking about correlation, and then lastly we will be talking about the difference between covariance and correlation, which one to use, which one not to use, and all those things. And in this video we shall be talking about correlation. What exactly is correlation? Correlation is similar to covariance. We studied about covariance in the previous session, in the previous video. Correlation is similar to covariance also for measuring how two variables are related or moving together. When two sets of data are strongly linked together, we say they have a high correlation. The word correlation is nothing but a combination of co and relation. Co means together and relation is relation. Correlation is normally positive when the values increase together and is negative when the values decrease together, as in one increases and the other decreases, right? A correlation is assumed to be linear following a line. Now, correlation is always ranging between +1 to -1, which means if I draw a graph like this, imagine you are analyzing height and weight. Now this is a clear case of very high correlation. Very high correlation where your correlation value will somewhere be near to 1. And in this case, as height increases, your weight also increases. Another case of correlation is something like this. You have height and weight. Imagine you have data like this. Somehow the data is scattered within this range, but you can see the positive correlation. You can see that they are moving towards the same direction. When the weight is increasing, the height is increasing as well. This is also a case of positive correlation, but it could be a low positive correlation. I'm not exactly sure about the exact value, but should be somewhere around 0.5 to 0.8 or something like that. Imagine a case where you are analyzing two features, height and weight, and the points are something like this, which is clear. When the height is increasing over the x-axis, the weight is decreasing. You can see a negative correlation here. Here, the correlation value will be somewhere near to minus 1. Could be like minus 0.5 or minus 0.3 or something like that. Whenever you see a graph like this, let's say height and weight, and the data points are randomly distributed. So nobody can sense whether there is an increasing trend or a decreasing trend. It's very difficult to interpret. In these kind of scenarios, we call it as no correlation or zero correlation. And normally in these cases, the correlation value is somewhere around 0. Exact numbers again are not known. Mathematically, there are ways to find the exact number, but visually it's not difficult. It's very difficult to interpret the exact value. But try to understand this thing, that correlation and covariance are almost similar to each other, but the only difference is covariance ranges from minus infinity to infinity, but correlation ranges from -1 to 1. And another big difference is that in correlation, both direction and magnitude are useful. That means if you are analyzing two features x1, x2, x3, x4, the correlation between x1 and x2 is 0.9, the correlation between x3 and x4 is 0.5. It clearly means that this is a stronger, it's not, my bad, it's not greater than equal to with the flow I just wrote, but it's quite evident that this relation is stronger than this, which is not the case in covariance. Your covariance value could be like 7, it could be 5, then you cannot clearly say whether this is a stronger relationship or not. That is the only difference between correlation and covariance. But which one to use, which one to not use in real life scenarios is something that is debatable. We'll be covering that in some of our future videos, but let's go ahead and watch out the correlation functions formula. Pearson's correlation coefficient P of xy is basically called as correlation of xy. The formula is very simple. It is covariance divided by standard deviation of x multiplied with standard deviation of y. In simple terms, this is nothing but covariance of xy divided by standard deviation of x multiplied with standard deviation of y. So here it is mentioned as variance of x and variance of y, and we all know that standard deviation is nothing but variance square, right? So variance is nothing but your, sorry, my bad. Standard deviation nothing but root over of variance. My bad, right? So this is your standard deviation x and standard deviation y. Now we'll try to take this formula and try to solve the same problem which we were trying to solve in the covariance thing. In the covariance chapter, if you remember, then the covariance was calculated as 7.45. I still remember this. Let me write down the covariance formula as well. Covariance of xy was nothing but 1 by n minus 1 summation of x minus x bar multiplied with y minus y bar. I still remember this part was 29.8 and again divided by 4, which was 7.45. Right. Now we'll try to solve correlation. In order to solve correlation, we have to find the sigma of x and sigma of y. What is the formula of sigma? We all remember it's summation of xi minus mu square divided by n minus 1 root over. So again we'll write it down, x, y, 3, 2, 6, 1, 0, 5, 4.5, 9, 1, 1. What was x bar? X bar was 2.4 and y bar was 4.1. So what is x minus x bar? 3 minus this, which is 0.6. I'm just repeating all these things. This was already calculated. 3.6 and minus 1.4 and minus 2.4. Y minus y bar was 0.9, 0.4, 4.9, 3 minus 3.1 minus 3.1. Let me just rewrite it. Minus 3.1. Done. So we will calculate the numerator part, which is x minus x bar square. And again, we will do the same for y minus y bar square. What is x minus x bar square? 0.36, 0.16, 3.6 into 3.6. It is 12.96. 1.4 into 1.4 is 1.96. 2.4 into 2.4 is 5.76. Similarly, this one will be 0.81, 0.16, 4.9 into 4.9 is 24.01. This is 3.1 into 3.1, 9.61 and 9.61. So we'll try to calculate this. So summation of this is nothing but 0.36 plus 0.16 plus 12.96 plus 1.96 plus 5.76 is 21.2. What is the summation of this? 0.81 plus 0.16 plus 24.01 plus 9.61 plus 9.61, which is 44.2. So what will be sigma of x, the standard deviation of this? We know the numerator, 21.2 divided by 4 root over, which is root over is somewhere around 2.3. Sigma of y will be 44.2 divided by 4 root over. 44.2 divided by 4 is around 11.05 root over 3.3. Done. Y4, because this is sample data, right? Now coming back to Pearson's coefficient, which is covariance divided by standard deviation of x multiplied with standard deviation of y, which is 7.45 divided by 2.3 multiplied with 3.3. So what is the value? If I calculate 7.45 divided by 2.3, which is 3.23 divided by 3.3, which is 0.98, which clearly means that they are heavily correlated, or largely positively correlated. Now let's try to draw the graph. Let's say x1, which is my stock 1, and the y, which was my stock 2. So let's say 1, 2, 3, 4, 5, 6, and let's say here 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And this is 1, 2, 3, 4, 5, 6. So the first one is 3, comma 5, which is 3, comma 5 somewhere here. 2, comma 4.5. 2, comma 4.5 somewhere here. 6, comma 9. 6, comma 9 somewhere here. 1, comma 1. 1, comma 1 somewhere here. And 0, comma 1. 0, comma 0, comma 1 somewhere here. So this is how my different points looks like. Obviously, it is quite clear that they are positively correlated. That means when my stock 1 goes high, my stock 2 also goes high. Now you know whether when you are analyzing the stock market, if there is a positive correlation or a positive covariance, at least when it comes to correlation, if the correlation is something like this, and if you're investing in stock 1 which goes up, you know which stock to play around. Well, pun intended, I was just joking. So that's all about covariance example, but we were trying to solve the correlation part. So the wording here is a little bit different. The wording here is covariance example because we were taking the same example, but we kind of use this same example to calculate the Pearson's correlation, right? So in this case, for stock 1 and stock 2, the Pearson's correlation comes around as 0.98. Talking about the interpretation of correlation, we all know correlation values ranges from -1 to 1. So when you are analyzing data, your values could range somewhere between that. Let's just talk about the positive case scenarios where I'm talking about 0 to 1. When you have a number like this within a range of 0.7 to 1, then we say that strong linear relationship. When there is a value within the range of 0.3 to 0.7, moderate linear relationship, and 0 to 0.3 is a weak linear relationship. That means weakly positively correlated. And similarly the other way around, right? Minus 0.3 to 0 could be a weak negative. Minus 0.3 to minus 0.7 again could be a moderate negative relation. Minus 0.7 to 1, sorry, minus 1 could be a strong negative correlation. In these kind of scenarios, you could assume the data points would be something like this. When one increases, the other decreases. Applications of correlation. There are humongous applications of correlation. To be very honest, correlation is one of the strong statistical concepts that we use in exploration of data. While analyzing data, while doing the data analysis, correlation plays a very vital role. Obviously, you will be taught about EDA and all those concepts. So here, one question is explore what are the variables that are correlated among a large number of variables. You have 100 variables about a person. Which one is related to their online purchase habit? So in that case, what you can do is number of online purchases. That's your variable 1, and one by one you can analyze the Pearson's correlation between age and this. For gender also, you can probably convert it into numerical values and then find the correlation, or average daily time, monthly income. So all this can be done. With the help of Python, it will take you hardly 1 or 2 lines of code to understand the correlation. And of course, using various correlation, you can also plot some beautiful heat map diagrams to understand everything. So all these concepts will be taught slowly. That's all about this particular session on correlation and covariance. That's it. See you in the next video. Bye bye. In this video, we shall be doing a small debate around the difference between covariance and correlation. However, we understood each and every concept. We know what is covariance, we know what is correlation mathematically and non-mathematically. In this video, we will be doing a small difference between each one of them and we'll try to see the difference. Covariance and correlation. The meaning is almost similar to both. Both of them measures how two variables are moving or related to each other. If you see a positive covariance, then your A and B are moving in the same direction. If you see a positive correlation, A and B are moving in the same direction. If you see a negative number, A and B are not in the same direction. If A increases, B decreases, and vice versa. Same goes with correlation also. So definition wise and the meaning wise, both are similar. I would not say same, both are similar. Value wise, of course, covariance ranges from minus infinity to infinity. It could literally be any number, 7.5, minus 1.5, minus 9.1, 8.9, and so on. But correlation always lies between minus 1 to 1. If it is closer to minus 1, highly negatively correlated. If it is closer to plus 1, highly positively correlated. If it is near to 0, then no correlation. Direction. Direction wise also both are same. Positive or negative represents how two values or two variables are moving together. Magnitude wise is where the difference comes. Magnitude wise covariance is not useful. It does not indicate the magnitude of the relationship, which means if you are having four variables x1, x2, x3, x4, it could be anything, age, salary, tenure, something else. If x1 and x2 covariance is 5, x1 and x3 covariance is 7, x1 and x4 covariance is 3, that does not mean that these two are having a strong relationship as this. But in the case of correlation, if x1 and x2 are having 0.9, x1 and x3 are having 0.7, and x1 and x4 are having 0.3, it is quite clear that this is a stronger relationship than this, which is a stronger relationship than this. So the value represents how strong the relationship is. Can compare for a different group of variables based on the values. Example, whether AB have a strong relationship compared to AB. No. And this one will be yes. That's all about the difference between covariance and correlation. The more you jump into the practicals part, you will have more understanding on which concept to use, which one not to use. But most likely and majorly in the field of data analysis, when you are analyzing multiple parameters, multiple features, variables, correlation is something that is highly used. But from the terms point of view, just make sure you also understand what covariance is all about. That's all about this particular video, and this potentially comes to an end to this module. See you in the next video. Bye bye. In this video, we shall be talking about hypothesis testing. What is hypothesis testing? Hypothesis testing is a statistical method that is used in making statistical decisions using experimental data. Hypothesis testing is basically an assumption that we make about the population parameter. I hope everybody knows about population and sample. So hypothesis testing is basically an assumption that we make about the population parameter. For an example, you say the average student in a class is 40 or a boy is taller than girl. All those examples we assume need some statistic way to prove. We need some mathematical conclusion, whatever we are assuming is true. What if somebody says you that the average height of people in Japan is 170 centimeters. How are you going to prove it? That's a hypothesis that you are building. So we need some mathematical conclusions. We need some conclusions that has to be statistically proven. And because of that only we are using hypothesis testing. Why do we use it? Hypothesis testing is an essential procedure in statistics. A hypothesis test evaluates two mutually exclusive statements about a population to determine which statement is best supported by the sample data. When we say that a finding is statistically significant, it's thanks to a hypothesis test. Which are the most important parameter of hypothesis testing? Well, the image that you see on the screen is something related to normal distribution. I hope everybody is clear with these concepts of normal distribution. This is basically a standardized normal distribution because the center line you see is 0 and then you see plus minus 1, plus minus 2, plus minus 3. Right? Anything lies that beyond plus minus 3 standard deviation or beyond plus minus 3 z score is basically your outlier. Anyways, getting back to the topic of hypothesis testing, there are majorly two types of hypothesis under hypothesis testing. The first concept is null hypothesis, and the second concept is alternate hypothesis. Let's try to understand each one of them. Now that we are talking about inferential statistics, in inferential statistics, the null hypothesis is a general statement or default position that there is no relationship between two measured phenomena or no association among groups. In other words, it is a basic assumption or made based on domain or problem knowledge. What if you say that the company's production is 50 units per day? That becomes your null hypothesis. So the company's production is 50 units per day. That means if the company's productions is proved that it is not 50 units per day, then you'll probably have to reject your null hypothesis, right? Talking about alternate hypothesis, obviously alternate hypothesis is the opposite of null hypothesis. The alternate hypothesis is the hypothesis used in hypothesis testing that is contrary to the null hypothesis. It is usually taken to be that the observations are the result of a real effect with some amount of chance variations superposed. Anyways, so alternate hypothesis example will be the opposite of null hypothesis, which in this case will be the company's production is simply not equals to 50 units per day, right? So there are some general fundamentals behind null hypothesis and alternate hypothesis, general assumptions, my bad. So what are those assumptions? The assumptions are null hypothesis can have equals to, greater than equals to, or less than equals to in their statement. So equals to, greater than equals to, or less than equals to. Alternate hypothesis should not have all those things. They should have not equals to, less than, or greater than. Try to remember this statement, which is very easy to remember. Now, talking about a case study or one simple statement that a company has made. Let's say Amazon claims that their revenue last year was at least $14 billion. At least 14 billion. That means either 14 billion or greater than that. So in that case, your null hypothesis will be Amazon's revenue last year was greater than equals to $14 billion. So the null hypothesis is the same and alternate hypothesis is the opposite of that, which is less than 14 billion. So your H0, which is nothing but your null hypothesis, is basically your revenue is greater than equals to 14 billion, and H of 1, which is your alternate hypothesis, is less than 14 billion. So this becomes your h1 and this becomes your h0. My bad. So there is a small change here. My bad. Right? So this is your h0 and this is your h1. Now what if similarly, let's say Amazon's revenue last year was at most $14 billion. That means either it was less than or equals to 14 billion. It was not beyond that, right? In that case, your symbols will change here, right? So, based on the statements, we can define our null hypothesis and alternate hypothesis. So that's all about the basics of null hypothesis and alternate hypothesis. In the next video, we shall be talking about some tailed tests. See you in the next video. In this video, we shall be talking about the two types of tests that we perform in hypothesis testing. So one of the tests is called as one-tailed test and the other test is called as two-tailed test. Now, the difference between each one of them is super simple. One-tailed test, a test of a statistical hypothesis where the region of rejection is on only one side of the sampling distribution, is called as a one-tailed test. Now, for example, a student has greater than equals to 800 marks or math score is greater than equals to 80%. So what is the area of rejection? The area of rejection is simply the opposite of it, which is less than 800 marks or less than 80%, which is one side of your graph. And that is one of the reasons we call it as a one-tailed test. Similarly, a two-tailed test is a statistical test in which the critical area of a distribution is two-sided and tests whether a sample is greater than or less than a certain range of values. If the sample being tested falls into either of the critical areas, the alternate hypothesis is accepted instead of the null hypothesis. Now, for an example, the student's total marks is not equals to 800. Now, there are two probabilities here. If they are not equals to 800, that means we accept the hypothesis, right? If it is not equals to 800, it could be less than 800 or it could be greater than 800. So there are two chances of rejecting this statement. It could be less than 800, it could be greater than 800. So this is a two-tailed test, right? So that's all about the simple definition between one-tailed test and two-tailed tests. We basically consider these both tests while performing any kind of statistical tests in order to have an hypothesis testing. So once we jump into the practicals part, we'll be able to showcase and let you know in a better way. See you in the next video where we will be jumping into the difference between p-value and significance value. Hi. Welcome to this module on statistics, and in this video we shall be talking about the two types of tests that we perform in hypothesis testing. So one of the tests is called as one-tailed test and the other test is called as two-tailed test. Now the difference between each one of them is super simple. One-tailed test, a test of a statistical hypothesis where the region of rejection is on only one side of the sampling distribution, is called as a one-tailed test. Now, for example, a student has greater than equals to 800 marks or math score is greater than equals to 80%. So what is the area of rejection? The area of rejection is simply the opposite of it, which is less than 800 marks or less than 80%, which is one side of your graph. And that is one of the reasons we call it as a one-tailed test. Similarly, a two-tailed test is a statistical test in which the critical area of a distribution is two-sided and tests whether a sample is greater than or less than a certain range of values. If the sample being tested falls into either of the critical areas, the alternate hypothesis is accepted instead of the null hypothesis. Now, for an example, has the student's total marks is not equals to 800. Now, there are two probabilities here. If they are not equals to 800, that means we accept the hypothesis, right? If it is not equals to 800, it could be less than 800 or it could be greater than 800. So there are two chances of having of rejecting this statement. It could be less than 800, it could be greater than 800. So this is a two-tailed test, right? So that's all about the simple definition between one-tailed test and two-tailed tests. We basically consider these both tests while performing any kind of statistical tests in order to have an hypothesis testing. So once we jump into the practicals part, we'll be able to showcase and let you know in a better way. See you in the next video where we will be jumping into the difference between p-value and significance value. In this video, we shall be talking about p-value and significance value. Now, what exactly is significance value? The term significance value or significance level, or called as alpha, is used to refer to a pre-chosen probability. And the term p-value is used to indicate a probability that you calculate after a given study. P-value, where the p symbolizes probability. The p-value or calculated probability is the probability of finding the observed or more extreme results when the null hypothesis h of 0 of a study question is true. The definition of extreme depends on how the hypothesis is being tested. Let's try to take an example and try to understand more about the p-value. You have a coin and you don't know whether that is fair or tricky. So let's decide null and alternate hypothesis. The null hypothesis, which is h of 0, is considered that a coin is a fair coin. And h of 1 is that a coin is a tricky coin and alpha equals to 5% or 0.05. So we have already defined our significance level as 0.05. Now let's toss the coin and calculate the p-value, which is the probability value. Toss a coin first time and the result is tail. So the p-value is 50% as head and tail have equal probability, right? When you're tossing one coin, there are two outcomes. Either it is a tail or a head. So the p-value comes as 50%. Toss another time, the second coin, and the result is tail again. Now what is the p-value? The p-value is 25% because getting two tails out of flipping two coins is 25% because the four combinations are HH, HT, TH and TT. So getting a TT is 1 by 4, which is 25%. Similarly, the process goes on, third time, fourth time, fifth time. So toss 6 consecutive time and you got the p-value as around 1.5%. So second time when you are tossing, p-value is 25%. Third time, 12.5%. Fourth time, 6.25. Fifth time, 3.125. And sixth time, almost 1.5 times, 1.5%. Right? But we set our significance level as 95%, which means 5% of error rate is allowed. And here, as we see that we are beyond that level, that is our null hypothesis does not hold good. So we need to reject and propose that the coin is a tricky coin, which is actually. And that is all about this p-value and significance value. Why do we set the significance value as 95%? This is what statisticians has already set. Significance level of 95% is a preset value that many statisticians have already set. So we usually consider 95% as our significance level, which means with 95% confidence and 5% of error is allowed. That's all about the general concept behind p-value and significance level or significance value. In the next video, we shall be giving you a brief idea about the types of tests, and we will be showing you which type of test should be used in which type of data. See you in the next video. In this video, we shall be talking about the types of test. As we all know, there are different types of tests, one being t-test. Then we have the z-test. We also have Anova. We do have chi-square test, and finally we have the correlation test. We all know that these tests are the various statistical tests to kind of test our hypothesis. We usually start with a null hypothesis and an alternate hypothesis. We perform these tests to validate our hypothesis. Now, before getting into each of these tests, let's try to analyze and discuss about few scenarios. We already know data is majorly of two types, one being categorical data, which is your qualitative data, and one being your numerical data, which is your quantitative data. Again, talking further about qualitative data, there are two further types, which is nominal and ordinal. If you are new to these topics, definitely go back to some of our videos related to data and qualitative and quantitative data. You will get understanding on those kind of videos. Even we also discussed about various numerical types, which is discrete and continuous, right? We all discussed about these basic concepts. Now, getting started with this, imagine you want to analyze one categorical feature. Now, one categorical feature, let's take an example of gender. And you come across this situation where you know that there are two valid values in gender, which is F and M. F belongs to female and M belongs to male. Now, what is the best way of representing this data visually? The best way could be a bar graph, or it could be a pie chart as well, which can also tell you the distribution between F and M. But bar charts are highly recommended for categorical features. Similarly, talking about one numerical attribute, let's say we'll talk about age. Let's say you are analyzing age of multiple customers and somebody asks you, can you tell me the statistical information from this? Provide me all the statistical information. Try to do a memory refresher. Statistical information basically means understanding your Q1, Q3, your median value, your mean value, your maximum value, your minimum value, and so on. Right? Now, what is the best way of getting all this information? Probably by plotting a box plot. Similarly, if you want to make it more complicated, let's talk about two categorical features. Let's say gender and location. Again, what could be a better way of visualization? I would again pick bar graphs. Let's say we have two locations, Japan and India. So this is Japan and this is India, and this is how the distribution of female and male people are in different countries. Similarly, making things more complicated before going into the two numericals part, I'll talk about one categorical and one numerical. One example could be for categorical, let's take gender, and for numerical, let's take age or income. How do you want to visualize or analyze these kind of features? And in gender, we have F and M. How about for female, I draw a box plot, and for male customers, I also draw a separate box plot, and then I identify the statistical information from each one of them. Possible? Quite possible. Lastly, I'll talk about two numerical features. Now, let's say I'll talk about two numerical features. Okay, let's talk about two numerical features. We'll talk about two numerical features. Let's say age and salary. And let's say I plot something like this, where this is your age, this is your salary, and you plot some data points. So you can easily plot scatter plots to identify the relationship between age and salary. If it looks like this, probably the correlation between age and salary is high. If the graph looks like this, probably the correlation is low, or maybe you can call it as negatively correlated. If the data points are randomly distributed, there could be no correlation, right? That is all about the different types of data. Now, coming back to our topic. What we can do is, as there are multiple types of tests and multiple types of data, which test do we conduct for which type of data? So we'll try to draw a small graph, a small table. Let's say my first column is type, that says the type of data. The second, what we see. And the third one is the type of test. Talking about one categorical and then one numerical, then one numerical plus one categorical, then we have two categorical, and then we have two numerical. What we see when we analyze one categorical data, we see something like this. What we see in one numerical data, we see something like this, a box plot. In one categorical and numerical data, we see some box plots like this for multiple categories. For two categorical data, probably we see some bar graphs like this. And for two numerical, we see some scatter plots like this. So the type of test that we usually perform on one categorical data or one categorical feature is called as one sample test. Similarly, for one numerical data, t-test is recommended. T-test, Z-test, I will talk about the differences between these kind of tests in the next video, but t-tests and Z-test are almost similar. I'll talk about the differences in the next video. Similarly, when we talk about one numerical and one categorical, we talk about t-test, or you can also use Anova. Again, inside Anova, there are multiple subtypes of Anova, which is one-way Anova, two-way Anova, that we will again explore and see how Anova can be used. Talking about two categorical features, we usually go for chi-square test. And lastly, we go for correlation test. So this is an overall idea about which type of tests has to be used for which kind of data and how do we see the data. That's all about this particular video. I hope you enjoyed it. In the next video, we shall be jumping into each and every test and we'll try to implement that test using our dummy data in Excel. See you in the next video. Bye-bye. In this video, we shall be talking about the next test, which is t-test. In the previous video, we talked about z-test. In this video, we are going to focus on the t-test. Before getting into t-test, let me try to talk about the data. In this particular example, I am going to take two types of data. There are 10 female customers and 10 male customers, and each one of them has their ages mentioned here. Now, we are going to perform two types of tests. For the first thing, what we need to do is we are just going to focus on only these 10 female customers. So we will try to test to determine whether the female population mean age is significantly significantly greater than 30. That's going to be my case. Now, what is going to be my hypothesis? My null hypothesis is going to be mean is less than equals to 30, and my alternate hypothesis will be mean is greater than 30. So I'm only considering one sample. So we are doing a one sample t-test. Now, in order to accomplish this thing, let me just note down few other things as well. My significance level is as usual going to be 0.05. If my p is greater than 0.05, then we accept the null hypothesis, else we reject the null hypothesis. I think everybody is clear till here. Now, I'm going to only considering that this particular column, which is the first column, as we are doing one sample t-test. So what I will do here is I'll probably go ahead and click on data and go to data analysis. And here you can see there is an option called as t-test to sample assuming unequal variances. I'm going to do that, but before that I'm going to just create a dummy variable. Dummy variable is just created, it's just a dummy data because there is no option called as one sample t-test. So we are going to use two sample t-test, but we are going to use the second variable as this dummy variable. Once you click on OK, let me just empty all these records. Now this is how your original window looks like when you open the data analysis and open the t-test for the very first time. The first variable range will be this. The second variable being the dummy variable, the range will be this. I'm going to click on labels because my first selected data is the header. My hypothesized mean difference is going to be 30 because here the test is to determine whether the female population mean age is significantly greater than 30 or not, right? Now, output range, I will select this particular cell and click on OK. Now once this is done, this is how my test looks like. I'll probably delete this cell because it contains my dummy data, and I will rename it to one sample test. That's it. And instead of hypothesized mean difference, I'll note it as hypothesized mean. Everything else remains the same as this is a one-tail test. Let me just get it back to this side. Okay, as this is the one tail test and my p value is 0.052, which is greater than 0.05. So in this case, I'm going to accept the null hypothesis. So I will note it down as green. I'm going to accept the null hypothesis because the p value is greater than 0.05, and this is a one tail test. Now we will perform another test which is going to be for both these particular features. Now if I am considering both these features, what will be my new H0 or null hypothesis? My new null hypothesis will be there is no significant difference between the mean age of male and female. The same hypothesis we also used in the Z test. There is a significant difference between the mean age of male and female. Okay, this is my new hypothesis. I'll note it down here maybe, or else here. Okay, let's note it down here itself. Okay, no problem. So this is my hypothesis. Okay, now I'm going to use both these samples. So again, I will click on data analysis, click on the same thing. Here, let me remove everything first. The first range is going to be my all the female customers age. The second range is going to be all the male customers range. And then the hypothesized mean difference is going to be 0 because I'm going to consider two samples, female and male. So my hypothesized mean difference is 0 because my assumption is there is no significant difference between the mean age of male and female. That means the mean age of male is equivalent to the mean age of female. The output range is, I'm selecting this cell. Done. Everything else looks fine. I'll click on OK. And this is my two sample test for this. Here my p-value is also greater than 0.05. You can see the p-value is 0.07, which means it is greater than 0.05, which means we are going to accept the null hypothesis. And what is the null hypothesis? The null hypothesis is there is no significant difference between the mean age of male and female. I hope you understood both these aspects of t-test on how to perform t-test on a sample test, on one sample test, and how to perform t-test on two sample test. That's all about this particular video on t-test. In the next videos, we shall be talking about various other tests. See you in the next video. Bye-bye. And in this video, we shall be talking about our first statistical test, which is z-test. In the previous video, we talked about the general overview about the different types of statistical tests, and we also discussed which type of test is applicable for which type of data. For one categorical data, one numerical data, combination of numerical and categorical, two categorical and two numerical. There are different types of tests that we perform. The first test that we are going to see today is going to be on z-test. In order to perform this z-test, we have 10 people each who are female and male, and I have their ages. So we are going to perform our z-test. Now before getting into this, let's try to understand what exactly a z-test and what's going to be our null hypothesis and alternate hypothesis for this particular example. A z-test is used to compare the mean of two given samples and infer whether they are from the same distribution or not. We do not implement z-test when the sample size is less than 30. We know that here in this case the sample size is less than 30, so z-test is logically not applicable here, but we will try to apply and see and interpret if we applied z-test what would have been the scenario, whether we will accept the null hypothesis or reject the null hypothesis or something like that. Before getting into this problem, let us try to note down our null hypothesis. Before noting down the null hypothesis, I am repeating once again, this data is of 20 customers or 20 people, 10 females and 10 males, and I have their ages, different ages. So here my null hypothesis will be there is no significant difference between the mean age of males and females. And the alternate hypothesis will be the opposite of it. There is a significant difference between the mean age of males and females. In this particular example, I'm going to use the significance level as 0.05, which we already know that most of the statisticians use this significance level. So whatever p-value we will get from this z-test, based on that we will be deciding whether to accept or reject the null hypothesis. We already know the conditions. If my p-value is greater than 0.05, which means we have to accept the null hypothesis, and if p-value is less than 0.05, then we have to reject the null hypothesis. I hope everybody is clear on this thing. Now what I need to do is, before getting into that, let me discuss about the formula of the z-test. Z-test is basically your x1 bar minus x2 bar. X1 bar is your this mean age of female, x2 bar is the mean age of your males for the sample population. Mu1 is the mean of your population data for the female customers, and mu2 is the population mean of the male customers. Sigma 1 is our standard deviation for female, sigma 2 is the standard deviation of male, n1 is the number of count for the female customers, and n2 is for the male customers. Simple. So how to perform the Z test? I'm pretty much sure this option might not be visible in your Excel sheets. What you need to do right now is simply go to File and go to these options, and here you will be able to see add-ins, and here in my case this analysis tool pack is already activated. In your case you have to activate that pack. There are so many blogs and videos which you can take reference from and activate the pack. So once your pack is activated, you might have to restart your Excel. You just restart your Excel and get started with again. Now I will quickly jump into the Z test part. So I'm going to click on this data and then click on data analysis. You can see when I'm clicking on data analysis, I am able to see a lot of options that is related to data analysis. In this case, I'm going to perform the Z test to sample for means. Before getting into that, I would also need to calculate the variance of female and male ages. So here I will note down var1 and var2, and I'm going to calculate the variance of the female users, and same I will just drag it so that it will auto calculate for the male users. Now these are the two variances that we have. So 9.95 is the variance of female age, and for male age it is 14.32. So I'll click on data, go to data analysis. Now here I'm going to click on the Z test to sample for means. The moment I click, you can see automatically some of these values are auto populated because uh, I was kind of doing some practice just few minutes back. uh, so you, in your case, everything should be null, so you should look like, your window should look like this. How to get started? Click on this and then it will ask for a range of the first column, so pass it. Similarly for this, the range of the second column. As you have already included the headers, click on labels. By default, it will be turned off. Click on labels. My hypothesized mean difference will be 0 because I'm assuming that the population difference is 0. That's my assumption, right? That there is no significant difference between the mean age of male and female. So my hypothesized mean difference will be 0. The variable 1 variance will be 9.95. The variable 2 variance will be 14.32. Alpha is my significance level, which is set as 0.05. Where do you want the output? Let's say I'll click on this and click on this. That means I need the output in this cell. The moment I click on OK, you can see my Z test output is ready. Now how to interpret this table? It's very simple. The first is your mean value. So for female age, the mean value is 22. If you want to validate that, you can probably validate that in a different cell, and you can see the average of the female age is 28.2, and same, the average age of the male will be 25.9. The variance is already predefined. How many observations do we have? We have 10 observations. Hypothesized mean difference is 0. Now I hope everybody knows about one tail test and two tail test, right? Now in this case, you can basically consider any of this, either one tail or two tail, but in both the cases your p value is greater than 0.05, and as p value is greater than 0.05, which means we have to accept the null hypothesis. So in this particular example, we are going to accept the null hypothesis, and conclude that there is no significant difference between the mean age of male and females. And obviously the age of female is 28.2, age of male is 25.9. It looks little bit different from human point of view, but from this particular statistical test we conclude that there is no significant difference between the mean age of males and females. Now this is how you calculate your Z test using Excel. You can also perform this test using Python as well. So there are different strategies, different libraries that you will be using to calculate, which we might study in future. But as of now, that's all about this particular topic on Z test. In the next videos, we shall be talking about various other tests related to t test, correlation, chi-square, Anova, and so on. So see you in the next video. And in this video, we shall be focused on the last test, which is called as Anova. Anova simply stands for analysis of variance. It's a statistical test that is used to check if the means of two or more groups are significantly different from each other. It's a parametric test for hypothesis testing. Now, before getting into our hypothesis testing, talking about our null hypothesis or alternate hypothesis, I want to focus something on the parametric keyword. What do you mean by parametric and what do you mean by non-parametric? The key difference between parametric and non-parametric test is that the parametric test relies on statistical distributions in data, whereas non-parametric do not depend on any distribution. Parametric is a statistical test which assumes parameters and the distributions about the population are known. It uses a mean value to measure the central tendency, and these tests are common and therefore the process of performing research is simple. And talking about parametric tests, there are multiple tests which are parametric, including t-tests, z-tests, and Anova. So Anova is a parametric test as well. Now, getting deep into this particular example. As I talked about that Anova is nothing but a statistical technique that is used to check if the means of two or more groups are significantly different from each other. Now, let's talk about this particular example. As you can see, there are three types of groups: cholesterol lowering drug and cholesterol levels. So there are three groups which are given with different doses of drugs. Group A with 0 mg, Group B with 50 mg, and Group C with 100 mg, and these are the cholesterol level of multiple patients. Now, talking about this example, what should be our null hypothesis? The null hypothesis here has to be mean 1 equals to mean 2 equals to mean 3. In simple terms, there is no significant difference between mean values of each group. And my alternate hypothesis means aren't equal. That means there is a significant difference between mean values of each group. I hope everybody is clear with the null hypothesis and the alternate hypothesis. Now, there are certain things that we need to discuss here. One of them is sum of squares. Sum of squares, which is also called as SS, is nothing but it quantifies the variability within the group. Let me write down everything, and once we run the Anova test, I will have a better explanation about all these things. Degrees of freedom, which is also denoted as DF in statistics. Now, DF between the groups, and there is another concept called as DF within the groups. Now, DF between the groups, the formula is simple: number of groups minus 1. So what will be the DF between the groups in this particular example? it will be 3 groups minus 1, which is 2. And df within the groups is going to be number of observations minus number of groups, which in this case will be 27 minus 3, which is 24. My mean squared value, or MS, it is the average variation either between groups or within groups. The formula is MS equals to SS by DF. So done. Then comes your F statistics. F statistics, it is the test statistics in one-way ANOVA. F is basically MS between the groups divided by MS within the groups. MS is basically our mean squared value. Now talking about our final statement, if p-value is greater than the significance value or significance level, in that case we accept the null hypothesis, else not. And we all know what is our significance value is basically 0.05. Now let's try to call our data analysis operation and call the ANOVA. I'll click on data analysis and I will call on the ANOVA single factor. And here it is asking for input range. I will click on input range and then I will select everything. And as I have selected the labels as well, I will be checking the labels. My alpha value or my significance value is 0.05 and output range, I want it in this particular location. Click on OK, and this is how your ANOVA single factor summary and ANOVA table looks like. It is divided into two things. The first being your summary statistics, and the second being your ANOVA values. Now, summary statistics is quite simple. For each group, it has calculated the count and the sum. If you want to validate for group A, the sum is 2380 and the sum here is 2380. For group B, the sum is 2170, the sum is 2170, average is 241, average is 241. If you want to validate the variance, let's blindly validate the variance for my third column. And here you go, the variance is 411, which is 411. Everything looks good. Now comes the main table, which is ANOVA table. So my between the groups SS calculation is 14,007 and within the groups is 14,000. Now DF is 2 for between the groups, because between the groups formula is number of groups minus 1. Here we have 3 groups, so 3 minus 1 is 2. So that's why we have 2 here. Within the groups, it is number of observations minus number of groups. So 27 minus 3, which is 24. MS value is this divided by this. SS divided by DF. You can see this formula. The F value is 12, P value is 0.000243 and F critical value is 3.4. There are two ways to check your ANOVA scores, but as we are considering the P value, talking about the P value is way less than 0.05. So in this case, as my P value is less than 0.05, we basically reject the null hypothesis. If the p-value is greater than 0.05, then we accept the null hypothesis. As it is less than 0.05, we reject the null hypothesis. So we conclude that the means are not equal. So we are kind of accepting the alternate hypothesis. So that's all about this particular video on ANOVA. I hope you had a good amount of understanding on ANOVA, and that is how you check your ANOVA score in Excel. That's all about this particular video. See you in the next video. Bye bye. this video we shall be talking about the chi-square test, or people call it as chi-square test. Now, chi-square test is basically used for categorical data. Now, as I already told you that this test only works for categorical data, which means the data which are in categories. For example, gender, male or female, or color, red, yellow, green, etc. In this particular example, I have two categorical features, one of them being gender, which has two valid values, and one of them being location, which has three valid values, which is Japan, India, and Korea. Now, you can see the formula of chi-square is basically summation of observed minus expected value to the power of 2 divided by expected. Now, what is observed and what is expected value? I'll try to explain. So before getting into this problem, we'll try to create our null hypothesis and alternate hypothesis, because ultimately we are going to use chi-square in order to check and test our hypothesis. I hope everybody knows about hypothesis, as we already covered what is hypothesis. Simply a hypothesis is a statement that might be true, which can be tested. In this particular example, let me write down my null hypothesis, which will be there is no association between gender and location. The alternate hypothesis will be there is an association between gender and location. All good. If p-value is greater than 0.05, that means I will reject my null hypothesis. If the p-value is less than 0.05, that means I will accept my null hypothesis. Now comes the first thing, is what is O, what is E? O is basically observed values and E is basically your expected values. In order to find the observed values, I'll take help of pivot table. So I will ask the table range to be this and location of my output to be somewhere here. Done. My gender, I will drag it to my rows, location in my columns, gender in the values, and that's my pivot table. So I'll kind of copy paste this pivot table to create my observed values. So I'll just delete all these labels. I'll just take these values, okay? And here I will note it down as observed values. So these are my observed values. My female customers staying in India are 6, females staying in Japan are 6, females staying in Korea are 0. Males staying in India are 2, 2 and 4. This is my row total. I will write it down as my row total, and this will be my column total, and basically this value 20 is nothing but my grand total. Okay, simple. Now that's my observed values. Similarly, I will create another table for my expected values. I will empty all these records because I don't need all these things, right? Now, how to calculate the expected values? It's very simple. Expected values are nothing but row total multiplied with column total divided by grand total. Simple. That means the expected value for Indian female customers are the row total multiplied with the column total divided by the grand total, which is 4.8. Similarly, for Japan will be row total divided by this, multiplied with this divided by the grand total. Korea will be, the row total will be 12 multiplied with this divided by this, which will be 2.4. For male will be this multiplied with this divided by this is 3.2. And for male Japan will be this multiplied with this divided by this, which is similar to India. And for Korea will be this multiplied with this divided by this, which makes it 1.16. Everybody is clear with this table? I will simply copy this and paste it I will delete all these values because I'm not going to take help of that. And this particular thing is nothing but my this operation O. I will write it down as O minus E to the power of 2 divided by E. Okay, that's the mathematical expression, same as this one. So what will be this? This will be observed minus expected, give it a bracket, to the power of 2 divided by expected, that is 0.3. I will drag it for these three values and drag it for these three. Cool. So you can see, I'll repeat once again, this is nothing but my observed 6 minus 4.8, which is 1.2, to the power of 2, which will be 1.44 divided by 4.8. So O minus E to the power of 2 divided by E. If you want to validate this one, let's say for this one, it will be this value minus this value to the power of 2, which is 1.2 to the power of 2 divided by 3.2. Okay. Now, what will be my summation of this operation? The sum of this operation, my sum of this operation is nothing but, I will write it down here. This will be sum of all these values, which is nothing but 7.5. So this basically becomes my x square value. X square value. This is nothing but my chi square value. What will be my df, which is my degree of freedom? My degree of freedom formula is very simple. Degree of freedom is nothing but my row total, like the valid values in row minus 1 multiplied with column minus 1, which basically means how many rows do we have here? Female and male. Minus 1 is 1. How many columns do we have? India, Japan and Korea. Minus 1 is 2. So it will be row minus 1 multiplied with column minus 1. Okay. So DF value will be 2. 1 multiplied with 2. Now this is where I will calculate my p value. My p value formula is, I will use the chi square dot dis dot rt, which basically means it returns the right tailed probability of the chi square distribution. I'll call it, I will pass my x square value, pass my degree of freedom, press enter, and my p value is 0.02. I will try to create a table out of it. That becomes my p value 0.02, and as p value is less than 0.05, that means we are going to accept our null hypothesis, which means there is no association between gender and location. So my p value is going to be 0.02, which is less than 0.05. So our null hypothesis is going to be accepted, which means there is no association between gender and location. That is an end to this particular session on chi square. That's it. See you in the next videos for further topics. Bye. And in this video, we shall be talking about the correlation test. Now, we all know what exactly is correlation. Correlation and covariance basically helps us to tell how the linear relationship between two variables looks like. Covariance somehow ranges from minus infinity to infinity, and magnitude has no meaning to it. But if you see a positive covariance, you can probably understand that there is a positive relationship between the two variables. That means if variable 1 increases, variable 2 increases. And if you see a negative covariance, you can probably identify that when variable 1 increases, variable 2 decreases. But in the case of correlation, we all know that the value ranges from minus 1 to 1, and magnitude is very important, which means if you see a number very close to 1, let's say between variable 2 Let's say there are four variables: variable 1, variable 2, variable 3, and variable 4. If your correlation between variable 1 and variable 2 is 0.9, and the correlation between variable 3 and variable 4 is 0.8 or 0.6, which clearly means that this is a stronger relationship as compared to this. And other logics remains the same. if if it is a positive number, that means it's a positive correlation. If it's a negative number, then it's a negative correlation. And if it's a number very near to zero, that means there is no correlation. Now on the screen you can see two examples. One of them is some of the data points for a particular uh, from a particular set of customers. We have height and weights. And another example is again for certain amount of people, we have the age and salary. Now our task is to create or find correlation between height and weight and age and salary separately. These two are two different examples. Now again, to accomplish this operation in Excel, we need to again take help of data and data analysis. But before going into that, I just wanted to show you how the scatter plot looks like. The way you need to create a scatter plot is very simple. Just select your data, go to insert, go to recommended charts, and just click on this scatter plot. Now this is a scatter plot, which is your weight versus height. You can see the first data point is 140.61, which is this one. This is basically 156 and 65, which is this point. And this is how the plots has been created. Similarly, what I need to do is I will again do the same thing for age and salary. I will select the data, go to insert, go to recommended charts, and click on the scatter plot. And this is how my scatter plot looks like for age versus salary, right? Now in this particular example, you can see almost there is a positive correlation. Just looking at the data, I can quite say that there is a good amount of positive correlation, which means when your weight increases, your height increases, and vice versa. Even in the case of age and salary, you can see it's an increasing trend for sure, right? So how do we calculate the correlation value? So I'll go to data, I'll go to data analysis, and here I will click on correlation. And here it is asking for input range. What is my input range? I will just select this. Done. Labels in my first row because I have the headers. I need the output in this cell, and then I'll click on OK. And this is how the correlation looks like. So the correlation value between height and weight is basically 0.94. Similarly, I will also do the same thing for age and salary. Click on this. Instead of this, I will click on this. Done. Labels in the first row. Instead of this, I will click on this and click OK. And you can see that age and salary are also having positive correlation. So that is basically giving you an idea that both of them, in fact, height and weight are also positively correlated with each one of them, and age and salary are also positively correlated, and the score is even higher than this, which means age and salary are more, the bond between age and salary is more, the positive correlation is more as compared to height versus weight, right? That's all about this particular topic on correlation. On top of that, in case you don't want to go through this data and data analysis, there is also an inbuilt functionality that you can use, which is basically just click on equals to correlation. So correl is the function. Select the array 1 and then comma, select the array 2, and then you can see the correlation value is 0.94. Same for age and salary, I will do equals to correlation. The function name is correl, and then I will pass my first array, and then I will pass my second array, and then the value is 0.96. So this is how we analyze two numerical features. This is how we analyze two numerical features, and this is how we calculate the correlation. And based on the correlation test, we basically conclude whether there is a positive correlation between two variables or not. That's all about this particular topic on correlation test.